How's it going? I wish we were doing this in class, but you know, we're making it work. Can you turn in your booklet, I think it's page 7, and it says Newton's second law. Okay, it looks kind of like this page. Okay. So I wanted to talk a little bit about Newton's second law because it's probably the hardest law that people have the most difficulty trying to understand. Okay, so I'm going to write out some notes here and draw some pictures, and hopefully we'll have a better understanding of it. Okay, so the first thing it says is that for Newton's second law, the big equation that we're working with here is force equals mass times acceleration. Okay, so this is acceleration. Big M means mass because little m means meters, and this means force. Okay, and if you watch the brain pop video, which you should have, you would have seen this equation come up already. Okay, so Newton's second law has two different ways to look at it. There's a direct relationship and an inverse relationship or opposite relationship. Okay, so the first point says acceleration varies directly, oh, look at that color change, with the amount of force applied. Okay, and then the other part says acceleration, I'm just going to abbreviate it here. Acceleration varies or changes inversely with mass. Okay? It says mass of the body. Of the body doesn't matter. It's just the mass of the object. Okay? So, if force is constant when acceleration increases, mass must decrease. Okay, so this is an inverse relationship. Okay, so if you're like, Miss Labiuk, what's going on here? So if we were at the front of the class, I would have a ruler out, and that's why I have these little rulers drawn in your booklet, okay? So they look like here, like this, and then we have tick, 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 tick. And I would put giant Post-it notes on our rulers at the front, okay? There would be an F in the middle, an A for acceleration on one side, and a giant M for mass on the other. Okay, so this law is more about conceptual understanding than it is worrying about numbers. Okay, so here we're saying if force is constant, so whatever variable we're going to keep constant, I'm just going to circle. Okay, so if force stays constant, when acceleration increases, mass must also decrease. Okay, so as one goes up, the other goes down. So if you had a pen, okay, and this was force, mass, and acceleration, if force is staying the same, when I increase my acceleration, oh, look at that, my mass went down. If I increase my mass, oh, look at that, acceleration goes down. See, kind of like a teeter-totter, okay? And the same thing works the opposite, right? If our mass goes up and force stays the same, then acceleration goes down. So it's an opposite relationship. Okay? But if force or mass increase, the other variable will do the same. You probably figured that out, okay? Because it's a direct relationship. Okay, so again, here's my little ruler, right? I have M, F, A. My little ticks on my ruler, don't really matter. Okay, so here we're saying if force or mass increase, so that would mean here acceleration would be the constant one. If mass increases, then so does force. Okay, and vice versa. If force decreases, then mass decreases, then force will also have to decrease as a result. Okay, so if I think about my pen as this ruler, force is in the middle, mass is on this side, acceleration is on this side. If I keep acceleration constant, so I'm going to hold it. If I increase my mass, oh, look at that, force is also increasing. Okay, if I decrease my mass, oh, look at that, force is also decreasing. Okay, and this goes for keeping acceleration constant or mass constant as well. Okay, if I kept mass constant, if force went up, acceleration would also go up. If force went down, acceleration would also have to go down. Okay, so I tried to color code this. If we keep mass constant, it's in purple. If we did acceleration, it's in blue. Okay, now, so that's kind of like a way to think about the relationship, but we also can draw it. Okay, because remember we talked about how in physics, we want to be able to graph and understand what the graphs of different relationships or different things in physics, what's happening. So, for example, let's take a look here. We have a y and x-axis. We have three variables here: mass, force, and acceleration. Okay. If force is constant, it is not going to be changing. We're not changing it here. We're not looking for a result here. So force is not on this graph, okay? But if let's look at the red one here, okay? So if we increase our mass, what is happening to our acceleration, okay? So if we don't know what's happening to our acceleration, it goes on our y-axis. If we're changing it, it goes on the x-axis, okay? So when this is a inverse relationship, okay, that means that the lower the mass, okay, the higher our acceleration, okay? So the lighter an object is, the faster we're able to go. And the more it weighs, the slower we're going to be able to go. So the line looks like that. Okay. So this is what an inverse graph looks like for Newton's second law. It always has a line that goes down and to the right. Okay. How steep? You know, I don't know whether it's like this or like this or like this or even steeper, okay, but that's generally what it looks like, okay? And then it just depends here if your acceleration here or your mass is here, depending on the situation, okay? On the opposite way, a direct graph would look like this. Same, y and x-axis, and let's take a look here. Let's use the purple one, okay? So if mass is going to be constant, okay, then it's going to be force and acceleration that are going to change, okay? So let's say we change force, okay? So we're going to try and see what's happening to acceleration. That's the one we don't know, okay? So if force increases, so if we have a lot of force, that means we also have a lot of acceleration, okay? If we have a small amount of force, we're not pushing very hard, we're also not going to be moving very far or very fast, okay? So all direct relationships, okay, for Newton's second law look like this, okay? Let's give this a try with some actual examples so you're not like, what? And see if you get what's going on. Okay. It says, Newton's car is driving on a highway. After braking, it stops. What is happening to the force? Okay, so the first thing I do is I draw my little ruler. I'll just draw a straight line. Okay, I have A, F, M. Okay, and then I'm going to draw my graph over here. Okay, so let's look at what the question says. It says a car is driving on the highway. After braking, it stops. What is happening to the force? So what is happening to the force? Force we don't know. So force is going to be here on the y-axis, right? It's what we're measuring. Okay, and does the mass of the car change during this? No. Okay, so our mass stays the same. Okay, so we're saying after it brakes, what is happening to the force? So our acceleration is going down, which means our force is also going down. Okay, so that means acceleration is over here, okay, because that's the one we're changing. So when we had a high acceleration, we had a lot of force, but then as we slow down considerably, we have less force. Oh, sorry. High acceleration, high force. Ah, there we go. Okay, if we're going fast, we need a lot of force. And then as we brake, okay, less force is needed. Okay, this is a direct relationship, right? So the graph has to go up and to the right. Okay, let's take a look at a different one. A bungee jumper jumps off a bridge. As he's falling, his acceleration is increasing. What is happening to the force he creates as he falls through the air? Okay, so again, A, F, M, draw my graph here, okay? Okay, as he is falling, his acceleration is increasing. Okay, so we're told right away our acceleration is increasing. What is happening to the force? Okay, we don't know what's happening here, so that means force is going to go on our y-axis, okay, as he falls through the air. Does your mass change as you bungee jump? No. Okay, so this is going to be our constant. Okay, so mass does not appear here. Okay, so, and it is the acceleration that we are changing. So we're saying as we increase our acceleration, what happens to the force he creates, right? Well, when we have low acceleration, while we're still standing on the platform or just about to jump off, we have a low amount of force, okay? But as we fall, the longer we're falling, the faster we're going, which means we're also creating more force. Okay, so our graph would look like that. Okay, it's a direct relationship. Excellent. Okay. Next up, you're pushing a cart of groceries down the aisle at Sobeys. If you keep adding groceries, what is happening to your acceleration if you push with the same force? Okay, so acceleration, force, mass. Okay, graph. Okay, you're pushing a cart of groceries down the aisle. If you keep adding groceries, there we go, keep adding groceries, our mass is going to be increasing. What is happening to your acceleration? Don't know. If you push with the same force. Okay, so if my mass is going up, okay, because force is in the middle, right? Force is in the middle. If my mass is going up here, my acceleration is going down. Okay, so force is not on this graph. Here I'm going to be changing my mass, and I don't know what's happening with my acceleration. Okay, so when I have a small amount of mass, I can go very fast, okay? But as my cart gets heavier and heavier, it slows me down if I'm keeping the same amount of force, right? There we go. Maybe somebody piles in tons of bags of dog food, right? Quickly it would become apparent that if you kept the same amount of force, you would be slowing down, okay? Right on. So if we looked at these questions and we just want to write a sentence to show that we understood what was happening, okay? So for this first one, okay, as acceleration decreases, so does the force the car applies. Okay. Here, the bungee jumper. What's happening to the force he creates as he falls through the air? Okay. So as he falls through the air, his force is increasing, as is his acceleration. Okay, so the sentence helps me see that you understand what's happening here. So here, what's happening to our acceleration if you push with the same force, okay, as mass of the cart increases, the acceleration of the cart decreases. Okay, and what's interesting with these laws is that it's never just one in play at one time. It's often the first law and the second law and the third law and then the second law and then the third law and then the first law. They're all kind of happening at the same time. Okay. Two other quick ones. You are pushing a cart of groceries. Let's be honest, just pop chips and hot dogs down the aisle at Superstore. If your mom spots your cart and starts removing objects quickly, what is happening to your acceleration if you keep pushing with the same force? Okay, A, F, M. What is happening to your acceleration? We don't know. Pushing with the same force, that's staying the same. Okay, and what's happening to our mass? Your mom is taking everything out, so our mass is going down. Okay, draw my graph. Force is constant, acceleration I don't know, okay, and mass is here. So as my mass is low, my acceleration will be high, and the heavier my cart is, the slower I'm able to go. There we go. Okay, and the last one here, A, F, M. Okay, you're trying to push a stalled car out of a ditch. If your unhelpful friends jump into the car, not care, as you are pushing, what happens to the force needed? Okay, they jump into the car, so that means our mass is going up. Okay, what happens to the force? We don't know, and our acceleration is going to stay constant. Okay, so if our mass goes up, this means that our force also has to go up. That's also needed. Okay, so if I draw my graph here, mass is what is changing. I don't know how it's going to affect force. Okay, so the lighter my car is, the less force I'm going to need. But as my friends jump in, I'm going to need more force to push it out. Okay, so the heavier the car becomes, the more force needed to push it out of the ditch. Okay, right on. I hope you have a better understanding here of Newton's second law. Remember, here it's not necessarily so much about the numbers as it is about conceptually understanding what's going on. Okay, thanks.